we can apply the techniques of trigonometry in order to give us some new ways of understanding complex numbers. So recall that a complex number looks like a plus bi, where a is a real number, or where a and b are real numbers, and I is the imaginary unit. Now, this is one example of sort of imprecise or poor terminology in mathematics. The symbol I is no more or less imaginary than any other number, but it's called imaginary because it's not a real number, which is again a sort of poor piece of terminology, but there it is. The defining characteristic of the imaginary unit I is that I squared is equal to -1. Now we know that this is a property that isn't satisfied by any real number. If you take any real number and square it, you'll get a non-negative number. You'll either get 0 or a positive number. And so when we work with the imaginary unit I, we can find solutions to equations that don't exist just within the real numbers, because we can solve equations like x squared equals -1. The solution to that would be I. Now, there are lots of things that we can do with complex numbers. We can add them, subtract them, multiply them, and divide them by using the techniques of algebra, treating I usually simply as another variable, but whenever we see an I squared, turning it into a -1. So for example, if I take the two complex numbers 2 plus 3i and 4 minus 6i, and I want to multiply them together, well, I'll do that by using our standard distribution techniques whenever we multiply two terms together, or two expressions together with multiple terms. So we'll get 2 times 4 is 8, then 2 times -6i is -12i, and then 3i times 4 is plus 12i, and then 3i times -6i is plus -18i squared. Well, now we can simplify things down. So we get 8 minus 12i plus 12i, and then I squared becomes -1. So simplifying all this down, -12i plus 12i becomes 0, and then we get 8 plus 18, so we get 26. So we have that these two complex numbers multiplied together give us the number 26, or if we want to write it in the form of a complex number, we'll write it as 26 plus 0i. Now, because complex numbers are defined entirely in terms of a and b, called their real and imaginary parts, respectively, we can represent them on a two-dimensional grid, a two-dimensional plane. So, for instance, we could take the number 2 plus 3i and represent that on a plane which we set up like this, where the horizontal axis is called the real axis, the vertical axis is called the imaginary axis, and then if we want to describe a number like 2 plus 3i, we take 2, which is called the real part, and the 3, which is called the imaginary part, and use those to find a point in the plane which corresponds to them. We label the real axis with our normal number line, 1, 2, 3. Our imaginary axis we can label as I, 2i, 3i, and so forth, which means that we can label the number 2 plus 3i as this point right here. The point that sits immediately above the real value of 2 and immediately to the right of the imaginary number 3i. In this way, we have a one-to-one correspondence between complex numbers and points on the plane when we set up the axes this way. This is known as the complex plane. While the real numbers can be represented using a single line, the complex numbers are usually represented using a plane in exactly this way that we've just set up. Now, we can do a lot of things with imaginary numbers, just working with them this way using algebra. However, it turns out that there are certain things which are a little bit complicated to work out using this form of real numbers, or of complex numbers, I should say. For instance, if I want to know what 2 plus 3i raised to the 5th is, it's not just 2 to the 5th plus 3i to the 5th. And that's because powers don't distribute across sums. If I wanted to work out what 2 plus 3i to the 5th was, just using the algebra that we've had so far, I would need to take 2 plus 3i times 2 plus 3i times 2 plus 3i times 2 plus 3i times 2 plus 3i and do a whole bunch of distribution, a whole bunch of cancellation, and a whole bunch of simplification over and over and over again. We want a better way of doing it, and it turns out that we're going to be able to use trigonometry rather, combined with the algebra in order to give us a better way of understanding complex numbers, writing them down, and doing arithmetic with them, particularly multiplication and division. Addition and subtraction are most easily done using the standard a plus bi expression that we have already been working with. Multiplication and division are going to be better accomplished by using the trigonometric form of a complex number. So let's see how that goes. Let's take the plane again, but let's work more in the abstract here. Let's say that we've got this point a plus bi, and that means that we've got a number that sits above a on the real axis and to the right of b on the vertical axis. If we were to think of this as an xy plane, this would also be the point a comma b. Now, what we want to do is imagine that this is in fact an xy plane, and we're going to describe this point using a vector like this. And we're going to describe this vector in terms of the magnitude and the angle formed right here. So we'll call this r and theta here. So to every complex number, a plus bi, we have the vector a comma b. And in particular, we want to describe this vector in terms of the angle theta and the magnitude of it. So the magnitude of a comma b is called the modulus, or absolute value, of a plus bi. So in other words, if I want to know the absolute value of a plus bi, also called the modulus of a plus bi, well, that is by definition the magnitude of the vector a comma b, or in other words, it's the distance from the origin to the point a plus bi when expressed on the complex plane. So it's the square root of a squared plus b squared. So this is part of the information that we can use to describe the complex number a plus bi. The other one that we have is the angle theta. So the angle theta, or an angle theta, I should say, because of course there are many angles that will all point in the same direction. An angle theta that points in the direction of the vector AB is called an argument of the complex number a plus bi. So we've got two pieces of information that we can use to describe the complex number a plus bi. We can describe it using the modulus, that is the distance the point is away from the origin, and the argument, which is the direction that you have to travel from the origin in order to get to that point. So we have these two pieces of information, and we can actually work out exactly what a and b are in terms of theta, the argument, and r, the modulus. So if we look at the triangle being formed here, the right triangle that has an angle of theta inside it and r as the hypotenuse, we have that sine of theta will be the opposite side, which has length b, divided by r. And we have that cosine of theta will be the adjacent side of this triangle, which is a over r. And these also still apply even when a or b are negative. But of course, we can rearrange this to get that b is equal to r sine theta and a is equal to r cosine theta. You'll notice that this is very similar to what we were doing with vectors in the previous sections, where we had a direction and a magnitude and we wanted to figure out the components of that vector. That's actually exactly what we're doing here. So let's see how we can, or let's define the trigonometric form of a complex number using these formulas here. The trigonometric form of a complex number with modulus r and argument theta is cosine theta plus I sine theta. I'm sorry, needed the r on the outside, is r times cosine theta plus I sine theta. This is also sometimes abbreviated as r times CIS theta, standing for cosine plus I times sine theta. And it's just a more compact way of writing down the expression cosine theta plus I sine theta. Let's show why this is. If we have r times cosine theta plus I sine theta, this gives us r cosine theta plus I times r sine theta, which, based on the computations we just did, gives us a plus I times b, which of course we can rewrite as a plus bi. So let's see some examples. let's find the trigonometric form or a trigonometric form, I should say, of 1 plus I. So, as always, graphing out the situation is usually helpful. So let's see where we're looking at. Now, the point 1 plus I is going to sit here on the plane. It's going to sit 1 unit to the right and 1 unit up from the origin because its real component is 1 and its imaginary component is I. So then we're describing this, this complex number using this vector, which goes from the origin up to 1 plus I. Now, that means that we're going to need to know this angle and the magnitude of this vector, i.e. the modulus. Now, in this case, the direction, this angle is pretty clearly pi over 4. The line going from the origin up to the point 1 plus I is going to have slope 1, which we know is 45 degrees, or pi over 4. And so all we need to do is figure out the modulus. So the modulus of 1 plus I, the absolute value of 1 plus I, is by definition the square root of 1 squared plus 1 squared. So the real part of 1, and then the imaginary part, which is the invisible 1 sitting in front of the I, which gives us the square root of 2. So the modulus of 1 plus I is square root of 2. The argument of 1 plus I, or an argument of 1 plus I, is pi over 4. So we have that 1 plus I can be written as the square root of 2 times cosine pi over 4 plus I times sine pi over 4. Or as square root of 2 CIS pi over 4. And so that's the trigonometric form, or a trigonometric form, of the number, of the complex number 1 plus I. Let's see some more. Let's find the trigonometric form of the complex number, we want negative 2 plus square root of 3 plus square root of 3i. Oh, I'm sorry. Negative 1 plus square root of 3i, so that we get a nice nice angle out of it. We'll do some non-nice angles in a second. Once again, here we want to graph out this point. So we've got negative 1 square root of 3, and so our square root of 3i. So our complex number negative 1 plus square root of 3i is corresponds to this point on the complex plane. Now the vector that goes to it looks like this. And to figure out the angle that's associated there, well, we can look at this triangle that we have formed here. We have that this side has length square root of 3, this side has length, well, 1, but in the leftward direction is negative 1. And so we can recognize this as a 1, 2 square root of 3 triangle, which means that this interior reference angle is going to be pi over 3. Now that tells us that the angle coming over from a standard position will be 2 pi over 3, because it's pi minus pi over 3. So we have, in this case, that we can read the modulus and the angle directly. So we have that the modulus of 1 plus square root of 3 is 2. And we have that the argument of negative 1 plus the square root of 3 is 2 pi over 3, or that's at least one of them. So that means that the trigonometric form, a trigonometric form of -1 plus the square root of 3i is 2 times cosine 2 pi over 3 plus I times sine 2 pi over 3, or 2 CIS 2 pi over 3. All right, let's do another one with numbers that don't give us such a nice angle. So let's find the trigonometric form of -2 minus 6i. Sketching things out, that's going to be in the third quadrant. So we'll have -2 on the real axis and -6i on the imaginary axis. And they give us the point -2 minus 6i, which sits here. So we've got this vector, which we're using to describe the point -2 minus 6i. In this case, the modulus is going to be easier to work out than the argument, so let's do that first. So the modulus of -2 minus 6i is, by definition, the square root of -2 squared plus -6 squared, which gives us the square root of 4 plus 36, which is the square root of 40, which we can write as the square root of 4 times the square root of 10, so we get 2 times the square root of 10 as the modulus for this number. Now, for the argument, finding an argument for this that's one of our standard angles is clearly not going to happen. None of our standard triangles that we have involve a square root of 10 anywhere inside them. So any expression that we get for this is going to have to use the inverse trigonometric functions. So there are various ways that we can work out the argument of this. However, the easiest way again uses the real and imaginary parts of the complex number. So notice that when I've got whatever my argument here is, theta, or maybe we're even going the other direction, maybe we've got a negative theta here, we have that if theta is the argument of a plus bi, then that means that tangent of theta is equal to b over a. And that's, of course, if a is not equal to 0. So what that means is that theta is either equal to, we can take either the inverse tangent of b over a, or we have that theta is equal to the inverse tangent of b over a plus pi. Now, the reason why we have these two options is because, of course, the inverse tangent only ever gives us values in quadrants 1 and 4. The inverse tangent of some ratio only gives us angles in quadrants 1 and 4. And so if we do have an angle which is in quadrant 2 or 3, as we do in this case, then we have to add theta to the inverse tangent here. So for us, we have that the argument of -2 minus 6i is equal to the inverse tangent of -6 over -2, which is going to be inverse tangent of 3. Now, inverse tangent of 3 gives us something in quadrant 1. Inverse tangent, here's inverse tangent of 3. But that doesn't give us the argument that we want. We want the argument going in the opposite direction. And so we need to add pi to this. We could also subtract pi if we wanted to. That would give us the negative argument here. But for us, we need to add the pi since our angle is in quadrants 2 or 3. If our angle was in quadrant 1 or 4, we could just take the inverse tangent of b over a, and that would be it. So in our case, the argument is going to be the inverse tangent of 3 plus pi. So that means that the trigonometric form of -2 minus 6i is going to be 2 times the square root of 10 times cosine of inverse tangent of 3 plus pi plus I times sine of inverse tangent of 3 plus pi, which we can write more succinctly as 2 square root of 10 plus CIS and I've run out of space, plus CIS of inverse tangent of 3 plus pi. Run out of space entirely. Also, that shouldn't have been a plus. Sorry, let me redo that. Equals 2 square root of 10 CIS inverse tangent of 3 plus pi. This allows us to find the trigonometric form of any complex number. So summarizing, the trigonometric form of a plus bi is r times cosine theta plus I sine theta, where r is the modulus of a plus bi, which is the square root of a squared plus b squared, and theta is equal to the inverse tangent of b over a if a plus bi is in quadrant 1 or quadrant 4, and theta is equal to inverse tangent of b over a plus pi if a plus bi is in quadrant 2 or quadrant 3. So converting from the a plus bi form to the trigonometric form is straightforward, and going the other way is even easier. So the rectangular form of r times cosine theta plus I sine theta is a plus bi, where a is equal to r cosine theta and b is equal to r sine theta. So going back and forth between the trigonometric form and the rectangular form, the a plus bi form, is fairly straightforward. Now at this point, we haven't seen the real advantage to using the trigonometric form of two complex numbers. But we do see it once we start looking at multiplying them. It turns out that there's a formula for multiplying two trigonometric complex numbers that we don't have with the rectangular form, which can simplify things, especially, as we'll see in the next section, when we want to raise a number to powers. So let's explore what happens. Let's let r times cosine alpha plus I sine beta and s times cosine beta plus I sine beta. Oh, whoops, I should have had sine alpha up above. Be two complex numbers. Clearly in trigonometric form. Now let's look at what happens when we multiply them. So if we take r times cosine alpha plus I sine alpha times s cosine beta plus I sine beta, and we're going to expand all this out, we're going to get a lot of terms. So first of all, we'll take the r and the s and bring them out in front, but then we have to multiply all these terms inside. So we get cosine alpha times cosine beta. Then we get cosine alpha times I sine beta. I'll write that as plus I cosine alpha sine beta. Then we'll get I times sine alpha plus I cosine beta. So that's I sine alpha cosine beta. And then we get I sine alpha times I sine beta. And that's going to be plus I squared sine alpha sine beta. Well, now we can do a few things. So first of all, this I squared here is just equal to -1, which means we can take these terms, the sine alpha and sine beta, over on the left and write this as cosine alpha cosine beta minus sine alpha sine beta. And those are all real numbers. They don't have any imaginary parts to them. So I'm actually going to put those in parentheses. Now, the two terms with i's in them, I'll factor the I out in front, and that gives us cosine alpha sine beta plus sine alpha cosine beta. Now, if you look at these carefully, what you'll notice is that each of these expressions is one of the expressions that tells us the sum, the sine or cosine of a sum or difference of two numbers. In fact, it's the sum in both cases. Cosine of alpha times cosine beta minus sine alpha sine beta is exactly cosine of alpha plus beta. And then we have I, cosine alpha sine beta plus sine alpha cosine beta is exactly sine of alpha plus beta. And so what we get is that the product of these two numbers, of the two numbers that we started with, expressed using complex number form, have a complex form that we can get by just multiplying the two moduli together and by adding the two arguments together. And this is what's amazing here, because multiplying two real numbers together, r times s, that's straightforward. And adding two numbers together, the two arguments, that's also straightforward. So in fact, the trigonometric form can simplify the process of multiplying numbers together, multiplying complex numbers together. So let's put this together in a theorem and try to write it down very clearly and then do some examples. So if z equals r CIS alpha, and or z1 equals r CIS alpha, and z2 equals s times CIS beta are complex numbers, then z1 times z2 is given by r times s times CIS of alpha plus beta. Remember, that means cosine of alpha plus beta plus I times sine of alpha plus beta. So this means multiplying two complex numbers together just involves multiplying the moduli and adding the arguments. So I'll mention that here. So we multiply the moduli and we add the arguments of the two complex numbers. And by a similar analysis, just a very similar computation to what we just did, If we want to divide the 2, then we divide the moduli times CIS of alpha minus beta, which means that we're going to divide the moduli and subtract the arguments. And this gives us a very efficient way of multiplying complex numbers together. So let's take an example. Let's take some of the numbers that we had before. We have that 1 plus I is equal to the square root of 2 times CIS of pi over 4. And we have that negative 1 plus square root of 3i is equal to 2 times CIS of 2 pi over 3. We worked that out earlier. So if I want to multiply the 2, if I want to take 1 plus I times negative 1 plus the square root of 3i, one way that I can do that is by writing them down in their trigonometric forms, using their moduli and arguments, and using the theorem above. If I multiply the 2 of these together, the way that I'll do that is by multiplying the arguments, the moduli together, which gives me 2 square root of 2, and then CIS of the sum of pi over 4 plus 2 pi over 3. Now, this we can work out further as 2 times the square root of 2 times CIS of, now pi over 4 is 3 pi over 12. 2 pi over 3 is 8 pi over 12. And so we get 2 times the square root of 2 times CIS of 11 pi over 12. And so this gives us an efficient way of writing down the product of 2 complex numbers. Now, we could also have written down the product of these 2 complex numbers using algebraic methods. We could also have written down, well, 1 plus I times negative 1 plus the square root of 3i is equal to, and then just expand it out. 1 times negative 1 is negative 1. Then we get plus the square root of 3i, 1 times square root of 3i, and then I times negative 1. So this gives us negative 1i, and then I times the square root of 3i gives the square root of 3i squared. So that'll give us negative 1. Now the square root of 3 times I squared is negative square root of 3, because I squared is negative 1. And then we get plus I times negative 1 plus the square root of 3. And so we can also multiply the two numbers this way. And interestingly, one of the things that we get is that these 2 numbers have to be the same. So in particular, this actually gives us another way of working out what the cosine and the sine of something like 11 pi over 12 are, although it's less efficient than some of the other ways that we have. So rather than do more on this page, let me show you what I mean on the next one. So we have now that 2 times the square root of 2 times CIS of 11 pi over 12 is equal to, let me make sure I get this right, negative 1 minus square root of 3 plus negative 1 plus square root of 3i. Yes. Now, if we divide both sides by 2 square root of 2, we get that CIS of 11 pi over 12 is equal to negative 1 minus the square root of 3 over 2 square root of 2 plus negative 1 plus the square root of 3 over 2 square root of 2 times I. Now, if we write out the left-hand side is cosine of 11 pi over 12 plus I times sine of 11 pi over 12. And that equals negative 1 minus the square root of 3 over 2 square root of 2 plus negative 1 plus the square root of 3 over 2 square root of 2 I. Now, as it turns out, the statement that two complex numbers are equal means that their real parts have to be equal and their imaginary parts have to be equal. So this means that in particular, we have that cosine of 11 pi over 12 is exactly equal to negative 1 minus the square root of 3 over 2 square root of 2. And sine of 11 pi over 12 is equal to negative 1 plus the square root of 3 over 2 square root of 2. So this is not actually showing us anything new because we could already have figured out cosine and sine of 11 pi over 12 using our sum and difference formulas, but it's an interesting way of seeing it all come full circle. We can also see what's going on or get a picture of what's going on graphically with this problem. So let's try graphing out the various numbers that we're using here. So let's do 1, 2, 3, negative 1, negative 2, negative 3, and I, 2i, 3i. And this will be a rough sketch of what's going on, but it'll get the point across. Now, one of our numbers was the number 1 plus I, and the other number was negative 1 plus the square root of 3i. And so I'll go ahead and do that in blue up here, and that's going to be approximately right there, negative 1 plus the square root of 3i. Now, in each of these cases, we had an argument and a magnitude. So we had 2 pi over 3 for the argument, and the magnitude was 2. And then for 1 plus I, we had an argument of pi over 4 and a magnitude of square root of 2. Now, if we look at the rectangular form of their product, we see that it's negative 1 minus square root of 3 plus negative 1 plus square root of 3i. So negative 1 minus the square root of 3 is going to be approximately there. And then negative 1 plus the square root of 3i is going to be about right there. And so this point right here will be our product, negative 1 minus the square root of 3 plus negative 1 plus the square root of 3i. Right here. And our argument here was 11 pi over 12. So we can visually sort of see what's going on if we write down our two initial points like this, 1 plus I and negative 1 plus the square root of 3i, with our angles, then in fact, multiplying them together on the level of the arguments, on the level of the angles, is simply putting the two angles together. It's just adding the two angles. So taking the 2 square root of 3 and then adding another pi over 4 on top of it in order to get to the result. So when we think about it this way, multiplying complex numbers is simply a matter, or is partially a matter of just adding angles to each other. So adding one angle to another to get the angle of their product. And then on the level of the magnitudes, the magnitude of the result is simply the product of the two magnitudes that we started with. So we see from this that multiplying two complex numbers is, at half of it, is just adding angles together. So the product is computed by doing an addition. And similarly, when we divide two numbers, that's going to involve subtracting angles, so moving backwards on the graph. And so we'll get that dividing two complex numbers, partially involves subtracting angles. And this process of multiplying two things together and computing that by adding something, or dividing two things and computing that by subtracting something, reminds us of how exponents work. So remember that if I take two expressions with exponents on them, 2 to the third times 2 to the fifth, the result is 2 to the eighth, because I've added the exponents together. So or actually let me make it really explicit here. So we see that a multiplication of two numbers is computed by adding parts of those expressions, just like we have in the trigonometric forms. Multiplying two complex numbers involves partially adding their two exponents, or arguments rather, together, just like exponents work here. This is part of the inspiration or rationale for a third way of expressing complex numbers. The exponential form of complex numbers is the following, or is given by the following. If I take the number e, the base of the natural logarithm, approximately 2.718, etc., and I raise it to the number I theta, this is defined to be cosine theta plus I sine theta, or in our notation from before, CIS theta. It's defined to be this. Now, the reason why we might want to define the exponential form this way, there are a few reasons, one of which I'll talk about in a second, but the main one is because this works with the formulas that we just worked out for what happens when you multiply complex numbers together. So let's suppose that I have r times e to the I alpha, and I multiply it by r e to the by s e to the I beta. There are two ways we can interpret this multiplication. The first is by simply treating all of this as if it were normal exponent manipulation. So using the rules of exponents, we can write this as, well, we can bring the rs inside, and then e to the ia times e to the ib will be e to the I alpha, or plus I beta, alpha and beta, not a and b, which we can, of course, write as rs e to the I alpha plus beta. But we could also say that this is r times cis alpha times s times cis beta, using the definition from up above, which gives us rs time, or rather, based on the formulas that we've had for how you multiply two complex numbers in trigonometric form, gives us rs times cis alpha plus beta. But then, using the definition that we just had up above, this gives us rs times e to the I times alpha plus beta. And you see that we get a full circle around here. So the reason why we might want to define an exponent involving an imaginary number in this way is precisely because it allows us to use the rules of exponents when working with complex numbers and have it be consistent with multiplication of complex numbers using the trigonometric form of it. So we can define e to the I theta this way and have it make sense. Incidentally, so first of all, this is known as Euler's formula. Euler was a very prolific and very famous mathematician who did a huge amount of work in all sorts of different fields and has many things named after him. In fact, E itself is called Euler's number. That's why it's given the notation E. Now, if we look at a specific form of Euler's formula with a specific theta, then we get a result which can be thought of, or has been described rather, as the most beautiful formula in all of mathematics. So, this is sometimes known as Euler's equation. Let's plug pi into Euler's formula. Euler's formula, which is e to the I theta equals cis theta. So, if we plug pi in, e to the I times pi will, by definition, be cosine of pi plus I times sine of pi. Well, we can work out each of those. Cosine of pi is -1. Sine of pi is 0. So we get that e to the I pi equals -1. This is one form of Euler's equation, although I prefer a slightly different one. If I add 1 to both sides, we get e to the I pi plus 1 equals 0. And this has been described, as I said, by many mathematicians as one of the most beautiful equations in all of mathematics. There's an amazing amount of content included here. There are some of the things that we like about it are the fact that in this equation, the 5 most important numbers in all of mathematics appear each exactly once. The 5 most important numbers in mathematics being 0, 1, e, I, and pi. All important for various reasons, but all central to mathematics and appearing all over the place. Also, we have each of the 3 basic arithmetic operations appearing exactly once. We have 1 addition, 1 multiplication, and 1 exponentiation. And there's a certain sublime beauty to this that many people who study mathematics and have worked with mathematics are very attracted to. So I would be remiss for not including Euler's equation in any discussion about complex numbers and the trigonometric forms of complex numbers. I want to end today with a little bit more justification for why Euler's formula here makes some sense. Now, I'm going to make reference to a few concepts that are from calculus. We're not going to prove any of them, but they're a little bit of foreshadowing and sort of explain where some of this comes from. So, in calculus, we can show the following. In general, if we have the equation, or the expression e to the x, it turns out that this is going to be equal to 1 plus x, and I'm going to write this in the following way. X over 1 plus x squared over 2 times 1 plus x cubed over 3 times 2 times 1 plus x to the 4th over 4 times 3 times 2 times 1, etc., etc. In fact, going on forever. This is a concept known as an infinite series, which, as I say, you treat in calculus, which we're which we're not doing here. But it turns out that we can get similar expressions for both sine and cosine. So if we look at the expression for cosine of x, we get 1 minus x squared over 2 times 1 plus x to the 4th over 4 times 3 times 2 times 1 minus x to the 6th over 6 times 5 times 4 times 3 times 2 times 1, etc., etc. So a similar sort of repeating pattern. And you notice that the expressions that occur in cosine appear in the expressions for e to the x, although some of them are negative. And then sine x is is x minus x cubed over 3 times 2 times 1 plus x to the 5th over 5 times 4 times 3 times 2 times 1 minus etc., etc. So we have these various series that where we can make the equations here explicit. Now let's look at what happens if we take e to the I theta in the expression up above and just plug in I theta here. We'll get 1 plus I theta over 1 plus I theta squared over 2 times 1 plus I theta cubed over 3 times 2 times 1 plus I theta to the 4th over 4 times 3 times 2 times 1, etc. Now, let's look at what happens in each of these. We get 1 plus I theta plus, now when we have I times theta squared, I is going to be a negative 1, or I squared rather is a negative 1. So that's negative 1 times theta squared over 2 times 1. Then we get I cubed. Now I times I times I is I squared times I. And I squared is negative 1, so that's negative I. So I cubed gives us negative I times theta cubed over 3 times 2 times 1. I to the 4th is I squared times I squared, which is negative 1 times negative 1, which is just 1. So we're back to theta to the 4th over 4 times 3 times 2 times 1, etc., etc. So now what I want to do is to group these terms up, gather all the terms that have i's together and all the terms that don't have i's together. Let's start with the terms that don't have i's. We get 1 minus theta squared over 2 times 1 plus theta to the 4th over 4 times 3 times 2 times 1 minus etc., etc. If we continue going on, grab all the terms that don't have i's, it's going to be all the terms that involve even powers of theta. Now we'll take all the terms that have an I in them and factor an I out. We never have more than a single I left after raising to powers, because anytime I have two i's multiplied together, they give me negative 1. So if we look at all the terms that have i's in them and factor an I out, we'll get theta minus theta cubed over 3 times 2 times 1. And then if we look at what the next term in this is going to be, we'll have theta to the 5th over 5 times 3 times 2 times 1, etc., etc. But notice that this expression right here is exactly cosine of theta. And this expression right here is exactly sine of theta. So this is exactly cosine of theta plus I sine of theta. And this gives another justification for why we would want to say that e to the I theta is equal to cosine of theta plus I sine of theta.